Hello everybody, my name is Volkans. I'm in the middle of building a Class D amplifier. These circuits are really great and there are lots of articles on how they work. And that's fine. But I thought, wouldn't it be nice to model and visualize the operation? So I grabbed the keyboard and started up my favorite IT tool, Excel. It may seem a bit unusual to use Excel for a task like this, but trust me, it works very well. And in my opinion, it's also worth to share the details with you.
So why Excel? It's a tool that you normally use to create price proposals, calculate your monthly income and expenses balance, etc. This means it is optimized to perform a lot of interdependent calculations quickly. And the discrete qualitative model that I built is at the core exactly this. A lot of calculations, each of which depends on the results of the previous. Then, when the calculations are done, it also provides a really powerful tool to visualize the results. The chart creator in Excel can do a lot more than you would think. But first things first, let's talk about how Class D amplifiers work. In one sentence, they switch the output transistors on and off very quickly.
We will talk about how this can be used to reproduce an audio signal in a second. But before that, just a few words about what advantages this operation mode has.
The key point is that the heat loss is very low. And the reason for this is that in order to produce heat, you need to have voltage over and current flowing through the same component at the same time.
If you use a transistor as a switch, this never happens. Okay, that's not entirely true. It happens, but to a far less extent than in an analog amplifier. But how will flipping a switch on and off create an analog signal? The answer is easy. Pretty much the same as your room light dimmer produces dim light. It turns your lamp on and off very quickly, so that the average power is somewhere between 0 and 100%. And it does this so quickly that your eyes do not realize what happens, you only see that the light is dimmed.
A Class D amplifier does the same, based on the audio signal. The output is turned on and off very fast accordingly. The amp uses a very high frequency triangle signal to decide whether the output must be turned on or off at a given moment. Compared to a light dimmer, there is a significant difference though. It is not your ears that calculate the average, but there is an actual filter for this purpose in the amplifier.
And that's the point where I decided to create a model in Excel. Because as simple as it sounds, it is not easy to visualize what actually happens in the circuit.
A model is a simple way to study the operation and also to check the influence of certain parameters on the result. And it's a much more fun project than summing up your monthly expenses. What we are about to create is a so-called discrete model. That means we model the operation at certain points in time and assume linear changes between those points. And in this case, the signals are not just discrete in time, they are quantized. This means, for example, a triangle signal will have only certain possible values. If we model the triangle signal in 10 steps, then it will only have values like 0.1, 0.2, 0.3 and so on. In reality, the signal is continuous. This definitely causes the model to deviate from the real-life behavior of the actual circuit, as it appears like we add the noise to the signal. The effect of this noise depends, of course, on the actual resolution. More triangle steps provide a more accurate model, with less noise and distortion.
So much about theory, and now let's go to the actual Excel stuff. I will not talk about how to calculate a sine wave in Excel. If you can't do it, you will most probably have problems understanding the rest of the video. So, before continuing to watch, make sure you know how to do it. Because we are at the point where it gets a bit more rough. As a start, how can we model a triangle wave? First, we need a series of numbers from 0 to like 500 or 1000 as the basis. These will be our discrete points in time.
There is a function called mod that calculates the remainder of a division. If we now divide our numbers with the number of triangle steps, we get a periodic list of numbers between 0 and the number of steps minus 1. Note that there is a factor 2 in the formula. It is used because a triangle signal will first go up and then go down. Without this factor, the resolution would only be half of the intended. The red curve shows the result. If we now subtract the number of steps, the curve will be shifted down, see the orange curve. In the next step, we calculate the absolute value of each number. This creates the actual triangle waveform as shown in the yellow curve. There are only two more things to do. to normalize the curve and to shift it again downwards. The lower green curve shows a triangle signal that oscillates between -1 and +1. Note that this is just a visualization. The actual data behind are separate dots, not a continuous line, as we discussed before. Modeling the operation of a comparator circuit is quite simple. Its output will be 0 or 1, depending on which of its inputs has a higher voltage. In the next step, we model multiple circuit elements at once. This is a qualitative model, so we can select constants as we like, but when designing an actual circuit, of course, these parameters must be calculated precisely. So what we do is changing the output dependent on its last value, plus the state of the comparators. This formula models the transistors, the power supply, and the low-pass filter consisting of a coil and a capacitor all at once. Although this is a very simple calculation, it models the operation surprisingly well. To be able to distinguish between the different signals on the chart, I shifted them. What we can immediately see is that the output signal has a certain delay compared to the input, and that it also has a bit of a zigzag contour.
I was curious about the delay, so I decided to add some functionality that automatically calculates the delay between the signals. And that's another point where the capabilities of Excel come in handy.
I mean, to calculate a lot of shifted curves and how much they overlap with one curve requires tons of operations. But hey, that's what Excel is intended for. There is a function called SumProduct that is not used too often. It allows to multiply arrays of numbers pairwise and sum the results. And this is exactly what I did to find the curve that overlaps the output best. If you have a model with 500 points and phase shifts between 0 and 100 steps, then 500 times 100, so 50,000 multiplications and additions need to be performed to find the best match. And this is done in an instant.
Here comes another one of my favorite Excel functions. It is one thing to identify which curve overlaps the best with the output signal, but it is a whole other thing to display the selected curve on the chart.
The indirect function helps us here. It works like a pointer in programming languages. Its parameter is an address, a reference to a cell, and it returns the content of the address cell. Once we identified which curve to display, we can create a reference to that curve. We calculate the column index, then use the concatenate function to create the whole cell reference, and use the indirect function to get the content. And we do this for all 500 points of the curve. Finally, we use a constant to set the amplitude to the same as the output curve.
At this point, we have a fully functional qualitative model that we can play around with. But before we do that, let's talk a few words about how our model relates to reality.
First of all, delays in model steps are not that informative. It is much better to convert that data to degrees. One period corresponds to 360 degrees. Second, if we assume a 200 kHz triangle signal and use 20 steps to model one signal period, then one model step represents a quarter of a microsecond in reality. And now it's time to run the model with different parameters. Although the results are really only qualitative, they exactly show why the components of an actual amplifier must be calculated precisely. As always, it is a compromise. A faster circuit produces more significant zigzags, while a slower circuit causes a higher delay in the output signal. The designer must find the ideal values to get the best performance. It is also very interesting to check the model under extreme conditions. I listed a few of these here. Go ahead and check them out. It's worth a shot.
If you like the idea, I really recommend to build up the Excel model on your own. It's a very good exercise and it helps to understand the structure of the model in detail. For those who are only interested in the result, you can download the Excel file from my website. Link is in the description. And that's all for today. I hope you enjoyed this video. Next time I plan to talk about how the actual amplifier turned out. See you soon!